Hello students, welcome once again to the course on manufacturing methods. In the previous classes we already had the introduction about the manufacturing methods. Okay, we have seen what are the various types of processing methods available, okay, and what are the different materials with which we can process the things. And in the last class we have discussed about the casting process. So we already had the discussion about the preliminary discussion about the casting, what are the different steps involved, what is like consider whole, what is the whole foundry process and all. Okay, similarly what are the advantages as well as limitation of this casting process, some different parts which can be manufactured by casting, that kind of exam we have taken. We have also seen different parts, cast parts, which are typical in a particular automobile, and we have seen that means right from the very big part to small parts like jewelry etc can be cast. And later on we have seen what is expandable mold process, permanent mold process, their advantages and all. Okay, and what is the like different parts which are there in the mold, so those things we have discussed. And what is chill, what is, you can say, parting line or riser etc, all those parts in a kind of the mold, those things we have discussed. And later on we have discussed about the gating ratio, which is very important concept. So in today's class we are going to discuss about the solidification behavior of different metals. Okay, that is solidification and cooling process in case of casting. As we have already discussed that in case of casting process, basically what we do is we melt the metal, and that molten metal we process with the molten metal. Okay, and that molten metal we pour into the mold cavity. Then we have said that we let it solidify or freeze, or you can say cool down, so that once again it reach to the solid state. So this solidification or cooling, sometimes we use the word cooling also, sometimes freezing also, this solidification or cooling, so it involves basically the transformation of the molten metal back into the solid state, because the ultimate product, that is the cast that we need, will be in the solid state. Okay, so now this solidification of metals, so the solidification behavior of metal, it is different, somewhat different for pure metal as well as alloys. As we already know, metals, it may be kind of pure metals, it may be alloys also. Okay, so first we'll be coming for the solidification of pure metal. So now in case of solidification, there are certain issues which we must know and we must consider. So certain issues which are associated with solidification, it includes, we must know about the time for a metal to freeze, whether whether there is shrinkage or what is the shrinkage behavior of that particular solidified metal or during the casting, and whether directional solidification is taking place, or if it is taking place, which it must, okay, in which direction or in which behavior basically it is working. As well as we have already discussed in the last class about the importance of riser in case of mold design. So what is the consideration of riser design with respect to the solidification time, those things we are going to see now. Now in case of solidification of pure metals, the first and foremost thing that we must know is the solidification, this pure metal, it gets solidified at a constant temperature, and that particular constant temperature is nothing but its freezing point. And in case of our solidification or cooling of that particular pure metal, this freezing point itself is same as that of its melting point. Okay, so if we go for this first figure where we have discussed about the cooling curve for a pure metal, so now in that particular curve, along the y-axis we show the temperature, and along the x-axis we show the temperature. So it's a plot of temperature versus time and temperature behavior for a particular pure metal when it is solidifying during the casting process. So now definitely we already know, initially when initial condition, basically the work, or you can say the process, will start with the pouring of the molten metal. So that means for our case this is the pouring temperature. Okay, then what will happen after it, we pour the molten metal and fill up the mold cavity, then we have to let it solidify. So once that is being done, then the solidification will continue, and initially what will happen, the liquid metal will cool down, but it will remain in the liquid state itself. Okay, and during this process, this is nothing but the liquid cooling region. Okay, and after that once it reaches this temperature, freezing temperature or freezing point, which itself is equal to its melting point. Okay, once that is being done, what will happen? The process of actual solidification will start, you can say. And during that particular time, what basically happens is, during this time, okay, so basically the metal's latent heat of fusion is being released to the surrounding. Okay, so from here to here there is a certain time that particular pure metal will cool down. Okay, and this particular time from when the freezing begins to when the freezing completes, this particular time is known as the total solidification time. And then we also have another time which is known as the total solidification time, and this total solidification time, it starts from pouring temperature, starting from the pouring of the molten metal to the mold cavity to the completion of the freezing. Okay, so this particular time is known as the total solidification time. Okay, and once the solidification is or the freezing is completed, so after that once again it will the casting product will cool down. Okay, and there will be a definite slope, and this particular temperature, this is particular known as the solid cooling. Okay, next, I hope all of you have understood this, and this is basically is known as the cooling curve for or pure metal. Okay, so in this particular case of pure curve, cooling curve, okay, pure metal cooling curve, basically what happens, we have to know what is the grain formation, at what way, which way basically grain is being formed. Okay, so the first thing is, this is the cooling curve. What we must remember is that the basic freezing in case of pure metal, it happens at a constant temperature. You can see this blue line is horizontal one. Okay, so there are three distinct parts. One is the liquid cooling region, when the metal is cooling down but it is at a liquid state. Then at this particular region, actually the latent heat of fusion which was previously there, that means if we consider from a solid state phase transformation from solid state to liquid state, then basically what happens, we supply the heat externally, and when phase change happens, basically there is latent heat that is being associated. Okay, so now once again here the phase change is happening. That means from liquid to solid it is coming, and during this particular phase, whatever latent heat it has previously soaked up for converting the phase from solid to liquid, that particular latent heat is being released to the surrounding. Okay, and here it gets completed, and after that we have the solid region here, and this is known as the solid cooling. Okay, so now in that particular case, what basically happens, if we consider with respect to, suppose if this is the mold, we consider, okay, mold cavity, and these are the walls, suppose, okay, surrounding walls. So now at this particular walls, the heat transfer rate is maximum. Okay, it is directly with respect to the ambient. Okay, it is associated with the ambient, so here the heat transfer rate is maximum. Okay, so what basically happens, once we pour the metal inside, so initially just with respect to the portion which is just nearer to the mold walls, so their solidification takes place at a higher rate. Solidification takes place means ultimately it is nothing but the cooling, or you can say giving off of heat. Okay, that means it is releasing the heat, giving away the heat, and now at this walls heat transfer rate is maximum. So initially there is a rapid development of some small grains, and there is a small, you can say small, this kind of, you can say cell. Okay, this kind of cell that gets formed. Okay, and there randomly oriented small grains are there. After that, what basically happens, these grains, this nucleation and grain growth, basically these grains, it grows, the growth occurs in a direction opposite to the direction of heat transfer. That means heat transfer is taking place in this direction, and grain growth will take place in this direction. Similarly for this wall, heat transfer is towards this, so grain will grow like this. Similarly for this, heat transfer is towards this, so grain will grow like this in this particular direction. So now in this particular case, so basically what basically happened, so initially some columnar grains, that means the grains which look like a column, they develop, and after that they sometimes form certain lateral branches, and this kind of growth is known as the dendritic growth. And this this kind of dendritic growth, it doesn't only occur in case of our pure metal, but also occurs in case of alloys. Okay, so there are sometimes like tree like structures. Okay, and during this course, okay, with respect to time, we consider the time, basically what will happen, this tree like structure, they are gradually filled in during the freezing. Okay, as additional metal is continuously deposited onto the dendrites until we get the complete solidification done. Okay, and these particular grains resulting from the dendritic growth, it takes on a particular preferred orientation. Okay, and in the mid, okay, this way. Okay, so here the grains are kind of coarse, okay, coarse size, and they are columnar grains, and they are always aligned towards the center of the casting. So from this, if you see, they are aligned towards the center, from this side towards the center, that side towards the center, and they are coarse grains. Okay, so right next to the, you can say, the wall, they are finer grains, small randomly oriented finer grains. Okay, and towards the end it is different. Okay, so this is basically it. So once again, this particular figure also shows similar kind of thing whatever we have discussed, development of columnar grains. Here it is a mold face. From this side, preferred oriented randomly, or you can say preferred growth direction of your columnar grains, it is be shown just near to the mold wall, it is small grains towards the higher grains. Similarly, this particular temperature, so figure shows how the temperature and consider the distance from the mold, how they are basically related. Okay, so next we have to go for solidification behavior of alloys. So now the basic difference between solidification of your pure metal and solidification behavior of alloy, it is that, so as we already know, alloy, it is nothing but a composition of materials. Okay, it's not a pure metal, that means more than one material it is there. Okay, so now depending on both the constituting metals, okay, so we get a particular alloy, and depending on that, over a range of temperature, basically this freezes, or you can say the the solidification of alloys occurs over a range of temperature, and that is what is the basic difference. Okay, so it doesn't undergo solidification at a single temperature, but rather it basically undergoes the transformation over a range of temperature. This is the temperature range. That means from here, freezing begins here. That means the freezing begins here. Freezing begins here, and over this temperature range, this much, okay, it continues, and it ends here. So it is a slope rather than being a horizontal line. So this is what is the basic difference between your solidification of pure alloys and solidification of, we can say, our not pure alloys, pure metals, and solidification of alloys. So now the exact range basically depends on the alloy system and what is the particular composition they have. Okay, so this particular figure A, it shows the phase diagram for a copper nickel alloy system, and figure B, it shows the associated cooling curve for this 50% nickel 50% copper composition during the solidification process during casting. Okay, so now this particular temperature, in this particular case, the solidification starts when we get the liquidus temperature, liquidus line. Okay, and it ends when it reaches the solidus temperature. Okay, so other thing, it is somewhat similar. We already have the pouring temperature. Okay, that means at what temperature we are going to pour. After that, we will have the liquid cooling region, just like this. Okay, and after that, once it reaches the liquidus, okay, so corresponding to this, the freezing will start here, and when the temperature reaches the solidus temperature, okay, then the freezing will complete. That means over this temperature range, the solidification has taken place. And once the freezing is over, that means it's just like in the previous case. Here also, during the course of solidification, it is basically giving off the latent heat of fusion, and the phase hence is taking place. Okay, and once this is over, after that there will be solid cooling. Okay, so now in this case, what basically happened, as we already know, it is taking place, the solidification is taking place over the range of temperature. Okay, so now here also within like one solid, you can say, uh, as temperature drops, okay, the freezing will begin at the temperature which is indicated by liquid dust, and it will be completed when we reach the solid dust. Okay, the start of the freezing, it's similar to that of the pure metal. Okay, here also a thin skin is formed at the mold wall due to the large temperature gradient and high rate of heat transfer there. Okay, and then freezing then progresses as just like the before to the formation of dendrites that will grow away from the wall. So the direction we have already discussed, okay, away from the heat transfer. However, owing to the temperature spread between the liquidus and solidus, that means there is a range. Okay, the nature of the dendritic growth is such that an advancing zone is formed here, in which both liquid as well as solid metal coexist. So this is one of the distinguishing features. Okay, so during this course, that means during this zone basically, okay, it will, the liquid and solid region, solid metal will coexist. Okay, the solid portions, they are like dendritic structure that are formed sufficiently, and it can trap small island of liquid metals inside the matrix. Okay, and this solid liquid region, now it is dendrite formation, it has become solid, and it can trap some island of liquids. Okay, so that means it becomes a solid liquid region, and so this solid liquid region, it has got certain kind of, it is of soft consistency, and that's why it is also named as massy zone. Mu, it is massy zone. Okay, it's a zone where solid and liquid coexist. Okay, and now just like the previous case, here also towards the just towards the, you can say, side of the wall, there will be this zone of small grains having random orientation. After that, this massy zone will be there. Okay, and sometimes segregation happens here. Okay, so segregation of different elements, it's a phenomenon, okay, which is prevailing in case of your solidification behavior of your alloys. Okay, and this cross section of the crystal, it is sometimes called as the, this segregation is known as the ingot segregation. Okay, so this is the basic difference between solidification of your pure metal and solidification of alloys. Okay, now in case of you might have heard about eutectic alloys. So solidification behavior of this eutectic alloys is somewhat similar to that of solidification of your pure metal. So I believe all of you already know, it is this eutectic alloy, it's nothing but it's a particular composition in an alloy system for which the solidus as well as the liquidus temperature, they are the same, they are having the same range. That means the behavior will be just like the case of solidification of your pure metal. Okay, so that you must remember. That means eutectic alloys, okay, so in case of eutectic alloy, the solidification behavior is somewhat similar to that of your solidification of pure metal. Okay, so for today, for this class, we stop here. Okay, and we'll meet in the next class. Thank you.